Hello everyone, welcome to Applied Chemistry Tutorials. Today we are going to talk about binomial theorem. So let's start with a brief introduction. We have discussed about classification, factorization and evaluation of polynomials in our earlier videos. You can check the link provided here. In this video we are going to discuss about expansion of higher order polynomials having a plus b whole to the power n format where n is a positive integer. This is known as binomial theorem of positive integral indices. Suppose we need to evaluate 1002 square or 99 cube. So we can rewrite them as 1000 plus 2 whole square and 100 minus 1 whole cube respectively. And then we can expand them using the algebraic identities for further calculation. So for 1002 square, we can rewrite it as 1000 plus 2 whole square and can use the formula a plus b whole square equals to a square plus 2ab plus b square. Similarly, for 99 cube, we can rewrite it as 100 minus 1 cube, and then we can use the formula a minus b whole cube equals to a cube minus 3a square b plus 3ab square minus b cube. But what about 999 to the power 5? So for this we need to know about binomial theorem. So let's discuss about the lower order polynomials first. So we know that a plus b whole to the power 0 equals to 1. A plus b whole to the power 1 equals to a plus b. A plus b whole square, we have learned it equals to a square plus 2ab plus b square. Similarly, a plus b whole cube equals to a cube plus 3a square b plus 3ab square plus b cube. In the similar way, we can calculate a plus b whole to the power 4, which equals to a plus b whole multiplied by a plus b whole cube. And now we can expand the a plus b whole cube term. So this equals to a plus b whole multiplied by a cube plus 3a square b plus 3ab square plus b cube. Now we can multiply the first term with the second term. A multiplied with a cube plus 3a square b plus 3ab square plus b cube will give us a4 plus 3a cube b plus 3a square b square plus ab cube. Similarly, plus b multiplied by a cube plus 3a square b plus 3ab square plus b cube will give us plus a cube b plus 3a square b square plus 3ab cube plus b4, and we can simplify them to have a4 plus 4a cube b plus 6a square b square plus 4ab cube plus b4. So we can have a plus b whole to the power 4 equals to a4 plus 4a cube b plus 6a square b square plus 4ab cube plus b4, and this can go so on and on. Definitely it will be time consuming to calculate higher order polynomials if we don't use the formula to expand them. Suppose we need to calculate a plus b whole to the power 7, so we need to do the multiplication again and again to find out what should be the expanded form. So from this we have some observations, so we are going to discuss them first. So the first observation is for a polynomial a plus b whole to the power n, the total number of terms will be n plus 1 after expansion. So let us take an example. We know that a plus b whole square equals to a square plus 2ab plus b square. Here n equals to 2. So we should have n plus 1 or 2 plus 1 which equals to 3 terms after expansion, and we can see it here. There are 3 terms, a square plus 2ab plus b square. Similarly, for a plus b whole to the power 4, we should have 4 plus 1 or 5 terms after expansion, and we can see that a plus b whole to the power 4 equals to a4 plus 4a cube b plus 6a square b square plus 4ab cube plus b4. Now the second observation is for a polynomial a plus b whole to the power n, power of a decreases by 1 and power of b increases by 1 in the successive terms after expansion. So we can see it here for a plus b whole square equals to a square plus 2ab plus b square. So here the power of a is 2. In the next term we have the power of a equals to 1. In the third term we have power of a equals to 0. Similarly, for b, the power of b equals to 0. The power of b here is 1, and in the third term we have the power of b equals to 2. And we can find it for a plus b whole to the power 4 as well. We can clearly see that power of a decreases from 4 to 3 to 2 to 1 and finally to 0, and power of b increases from 0 to 1 to 2 to 3 and finally to 4. And this can be found for all the polynomials. And the third observation is for a polynomial a plus b to the power n, the sum of indices of a and b is the same and is equal to index of a plus b. So here the index of a plus b is 2, and for all these terms we can have the sum of indices is 2. For 2ab also, for a is 1 and b is 1, so 1 plus 1 is 2, and for b square term also we will have the power is 2. For a plus b whole to the power 4 we can have the similar observation. So here the index of a plus b is 4, and here for the first term we have the power is 4. For 4a cube b we have 3 plus 1 equals to 4. For 6a square b square we have 2 plus 2 equals to 4. For 4ab cube we have 1 plus 3 equals to 4, and finally for b4 we have the power is 4. So now after explanation of all this observation we can talk about Pascal's triangle. When the index of a plus b is 0, and if we expand it, a plus b whole to the power 0 equals to 1, so we can say that the coefficient for the only term is 1. Similarly, when the index is 1, a plus b whole to the power 1 is a plus b, so the coefficient of a is 1 and the coefficient of b is also 1. For index 2, a plus b whole square equals to a square plus 2ab plus b square. So the coefficient of a square is 1, the coefficient of ab term is 2, and the coefficient of b square is 1. So from this we can observe some similarities. First of all, we can say that the first term and the last terms are always equals to 1. And secondly, the coefficient of a higher order polynomial can be calculated from the coefficient of a lower order polynomial. Here we can clearly see that 1 plus 1 will give us 2. Clearly we can see a relationship between these terms here. So let us verify this for the higher order polynomials. For index equals to 3, we should have a plus b whole cube equals to a cube plus 3a square b plus 3ab square plus b cube. So the coefficients are 1, 3, 3 and 1. So here again we can see the first term and the last terms are always 1, and this 3 is the summation of 1 plus 2 here, and again this 3 is the summation of 2 plus 1 here. So it's verified for index equals to 3, and we can go so on and on. For index equals to 4, so the first term will be 1, the last term will also be 1, and the second term will be 1 plus 3 equals to 4, the third term will be 3 plus 3 equals to 6, and the fourth term will be 3 plus 1 equals to 4. And for index equals to 5, the first term is also 1, the last term is again 1, and the second term is 1 plus 4 equals to 5, the third term is 4 plus 6 equals to 10, the fourth term is 6 plus 4 equals to 10, and the fifth term is 4 plus 1 equals to 5. Again, this is a very laborious process. Suppose we need to find out a plus b whole to the power 23. Then we need to calculate all the coefficients following this Pascal triangle method. So we need to figure out an easy way to calculate the coefficients. So for this we are going to introduce the formula of combination. So for non-negative integers n and r, if 0 less than equals to r less than equals to n, we can have NCR equals to factorial n divided by factorial r multiplied by factorial n minus r. Also, we need to know that factorial 0 equals to 1. So let us take an example. We need to calculate 5c3. So here n equals to 5 and r equals to 3. So factorial 5 divided by factorial 3, n minus r is 2 here, so multiplied by factorial 2. So we know that factorial 5 equals to 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, and factorial 3 is 3 multiplied by 2 multiplied by 1, and factorial 2 is 2 multiplied by 1. So after simplification we can have 5c3 equals to 10. So with that we can calculate other values as well. So 0c0 equals to 1. For index 0, we know that a plus b whole to the power 0 equals to 1, and the coefficient of that term is 1. So instead of 1 we can rewrite it as 0c0. Similarly, for index 1, a plus b whole to the power 1 equals to a plus b. So the coefficient of a is 1 and the coefficient of b is also 1. So we can rewrite them as 1c 0 and 1c 1 instead. For index 2, a plus b whole square equals to a square plus 2ab plus b square. So the coefficients are 1, 2 and 1. So we can easily replace them with 2c0, 2c1 and 2c2. And this can go so on and on. So 3c0 equals to 1, 3c1 is 3, 3c2 is 3 and 3c3 is 1. We can also calculate 4c0 is 1, 4c1 is 4, 4c2 is 6, 4c3 is 4, 4c4 is 1. And similarly for index 5 we can replace all the coefficients with 5c0, 5c1, 5c2, 5c3, 5c4 and 5c5. So let us write down the modified form of the Pascal's triangle. So for index 0 the coefficient was 1, so we can write it as 0c0. For index 1 we can write 1c0 for 1 and 1c1 also for 1. For index 2 we can have 2c0 for 1, 2c1 for 2 and 2c2 for 1 again. For index 3 we can have 3c0, 3c1, 3c2, 3c3. For 4 we can replace 1, 4, 6, 4, 1 with 4c0, 4c1, 4c2, 4c3 and 4c4. And for index 5 we can have 5c0, 5c1, 5c2, 5c3, 5c4, 5c5, and it will go so on and on. And now we can clearly see a trend and which can be utilized to write the binomial theorem. So binomial theorem for any positive integer n can be given as a plus b whole to the power n equals to nc0 multiplied by a to the power n plus nc1 multiplied by a to the power n minus 1 multiplied by b plus nc2 multiplied by a to the power n minus 2 multiplied by b square plus dot dot plus ncn minus 2 multiplied by a square multiplied by b to the power n minus 2 plus ncn minus 1 multiplied by a multiplied by b to the power n minus 1 plus ncn multiplied by b to the power n. And the proof of this binomial theorem can be obtained by applying principle of mathematical induction, and we are not going to show it here because we are going to focus mostly on the application part. That's all for today, and in the next video we are going to solve some problems related to binomial theorem. And till then please stay tuned with us, and if you like this video please give us a thumbs up and please subscribe to our channel. Thank you.